Great. Yeah, thank you so much for being here. It's a great pleasure to speak for this program. Now, the sort of interests and perspectives of all the participants into this program are quite diverse, and so I won't be able to speak to all of it, but I'll try to hit on a few different points and cover a few different aspects of this research thread for this program. The title you can see here is quite a mouthful, okay? But all the words are meaningful. So I'll try to, through this talk, I'll try to unpack the meaning of these expressions, and hopefully by the end it will all make sense. So to that end, let me start from the end with programmable quantum matter. Okay, what do we mean? And so first I will start by more conventional quantum matter, okay, non-programmable. So to fix ideas, you can think about a rock, okay, a chunk of matter, such as you might find outside if you go to the beach. And these systems are not programmable. Okay, they exist in a configuration of their own choosing. You don't get to choose that. Okay, this is a collection of atoms that choose to clump together in a particular way, based on conditions of temperature, chemical concentration, et cetera, that are chosen by nature. Okay? And you get to probe them in various ways. You get to control their state to some extent, but that extent is limited. Okay? So you can, for example, apply electromagnetic fields to this system. You can apply mechanical perturbations and so on. But this is a macroscopic system of, let's say, 10 to the 23 particles, and the number of knobs you have to control it is certainly much, much smaller than that. Okay, so you can apply some kind of coarse level of control to this system, and the same goes for measurement. Okay, the kinds of things you can measure here are somewhat limited and coarse-grained, broadly averaged over all of these unfathomable number of macroscopic constituents. For example, you can apply a potential difference to this sample of material, and you can run a current through it, and from that current you can back out a number, for example, a conductivity, that tells you whether this sample is a metal, an insulator, a superconductor, and so on. Okay, so this is one number that describes a collective state of many, many, many particles. Okay, and this is more or less what you can measure. I'm being a little schematic here, but just to fix ideas. Now on to programmable quantum matter. What do we mean? So this is a development motivated by the efforts to construct a quantum computer or a quantum simulator, okay? A system whose goal is to process quantum information. Okay? So even though these are being built with a purpose, okay, as computers, as a natural byproduct of that, we are beginning to have quantum many-body systems that look very, very different from that paradigm that we are more used to. Okay, so in this programmable world, what we have is a quantum many-body system that is built from the ground up, okay, by assembling elementary constituents. We're going to think about qubits. Okay, so each of these constituents is a two-level quantum system. It has two states, 0 and 1, and of course it's quantum mechanical, so we can put these states in superposition. Okay? And then we can assemble many of these qubits together and in this way form a quantum many-body system. Now many here is to be taken with a grain of salt. It's not 10 to the power of 23, it's maybe more like sort of tens to thousands perhaps at present. But it is entering a regime where at least the Hilbert space dimensions you can probe are very substantial, okay? And possibly difficult to simulate classically. Now, these systems differ from these more traditional ones in several respects, but certainly a key aspect is the fact that if we want to do computation with these systems, we require a level of control and measurement that is not available on sort of natural systems. Okay, so these are not things you're going to find outside on the ground. These are things that you need to build very carefully. And in particular, at the level of control, rather than having some limited number of knobs that we can use to control all of the constituents of the system, we demand the ability to go in and send detailed, spatiotemporally resolved instructions to all of these constituents. Okay, so what I'm going to draw now is a model of quantum computing, the circuit model, okay, which is a universal model of computation. If you haven't seen this before, I will explain in a second what it means. Okay, so this is a diagram where on the vertical axis I have time, okay, and on the horizontal axis I have spatial position. So these are my qubits at the beginning of the computation. And then the qubits simply continue to exist through time, okay? So these lines are the world lines of the qubits, okay, that exist throughout the computation. And then at certain times, I demand the ability to go in and dictate some interactions between these qubits. Okay, so for example, I can, at this moment in time, and for some duration, say tau, I want to be able to turn on some interaction between this qubit and this qubit, for instance. And then maybe also this qubit and that qubit. And I want to be able to do this in a way that is programmable at the level of single qubits or pairs or small numbers of qubits, and also resolved in time in this way. I want to be able to then switch this interaction off and turn on an entirely different set of interactions sort of a moment later. Okay? And this is, of course, not something that we can do here realistically. Okay? We cannot go in and demand that each of these 10 to the 23 particles do exactly what we want. Okay? So by repeating this kind of instruction enough times, we can run any computation we want. So we can visit, in principle, any point of the Hilbert space and really give rise to types of quantum dynamics that are very complex and very interesting. The second unique feature that these quantum many-body systems must exhibit in order to be useful computers is their ability to measure at a really, really microscopically resolved level. Okay, so if we want to use this for quantum computation, we want to in some way take advantage of the quantum mechanical Hilbert space, visit some highly entangled states during the computation. But at the end of the day, we want to return to a classical state that contains the answer to some classical questions we care about. Okay, maybe we're trying to factor numbers, we're trying to minimize some variational problem. We want to get a classical answer, and this requires making some very microscopically resolved measurements on all of these qubits. Okay, so when I draw these boxes later with this little meter, okay, this is meant to be like a meter that tells you the outcome of a measurement. This means that I'm making a complete measurement on one of these qubits, which returns a classical outcome. For example, these might be one configuration I get upon measuring all of these qubits. Okay, so this outcome is a string of n bits. Okay, so I take a snapshot of my quantum many-body state that gives me a classical bit string. And this might encode the answer to my computational problem. Now, again, this is very, very different from the kinds of measurements that we can normally do here, which, again, give us, let's say, one number or order one numbers that describe this collective state of many particles. And if you think about timescales here, okay, so I'm not saying what these qubits are, but depending on the specific technology we have, these timescales might be different. But if we think, for example, of superconducting qubits, okay, the technology that I guess won the Nobel Prize last week, these timescales might be on the order of microseconds, okay, the times that we need to turn on these interactions to implement a meaningful evolution there. And so if you think of running one of these evolutions on order maybe 100 qubits for order 100 cycles, something kind of realistic near-term experiment, you're getting out something like 1 bit per microsecond of computation. That's kind of a lot of data, like 1 million bits per second, or gigabytes if you're running this experiment for a few hours, let's say. So that's a lot of zeros and ones. You can fill up hard drives worth of zeros and ones, and the question is, what do we learn from that? Do we learn, of course we can just take a big average of all of this huge amount of data and recover something like observables that we're more accustomed to, these broadly coarse-grained observables that characterize this state in a coarse-grained fashion. But the question that motivates this program partly is whether in this huge amount of data we can discover some new universal phenomena that would not be visible in more traditional, let's say, condensed matter setups. So that's what we mean, or at least one of the things one might mean by the fine structure of quantum dynamics. Okay, so is there any new universal phenomenon to be discovered in this huge amount of finely resolved data? Okay. And so hopefully this clarifies the motivation for thinking about these problems. I'm going to now give an instance to show that this is indeed the case. Okay, at least as a matter of principle, we do have phenomena that emerge only in the setting, taking full advantage of these capabilities. So setting I want to think about now is called monitored quantum dynamics. Okay, and it refers to types of many-body evolution where there is an observer that is not just taking measurements at the very end, but is also intervening during the process, sort of asking questions to the system as the dynamics goes on. Okay, so I'm going to now draw another kind of instance here of dynamics. Okay, I will at some point stop drawing these circuits in detail, but in this one, let me draw out explicitly. So this looks exactly like that. However, now we introduce this new ingredient of measurements that take place during the evolution. Okay, so an observer might go in and interrogate the system, for example, here, let's say. Okay, so once again, these boxes here, let me color them. These are gates, unitary gates. Which are the elementary instructions we're sending to the quantum computer. And then these boxes instead, these are our measurements. Okay? And the model we're... Yes. One could think about different setups. Let me think about projection, so projective measurements. So each of these ones is going to yield an outcome that is binary, so it's 0 or 1, and it tells me which of the computational states my qubit was in. So it's exactly like these final measurements here. So this is very interesting in quantum mechanics because it doesn't just tell me the state of the system, but of course it alters that state dramatically in a non-deterministic and also non-local way. So it not only disentangles this particular qubit from the rest, but if this qubit was previously entangled to the remainder of the system, it might also non-trivially change the global wave function. This is some somewhat poorly understood process of wave function collapse. We're not going to solve the measurement problem of quantum mechanics today, but there are different interpretations of what that means. But certainly, practically, it's very clear mathematically what how to describe this phenomenon. Excellent. So each one of these outcomes again is this bit which we collect, and by aggregating all of the outcomes from all of these measurements, we will have a string of bits again, so analogous to this one, except now we've collected it sort of during the dynamics. And we have some number, let's say, k of measurements that we perform, and so there is this many possible strings. And each one of these possible strings of outcomes labels a possible wave function for the final state up here. Okay, so the overall many-body state. Now, this is a very interesting setup because it was discovered now 7 years ago, I guess, actually by folks here in Santa Barbara, that this setup exhibits a novel type of phase transition. Okay? And it's very in keeping with our program because it's a transition that is completely invisible to the coarse average structure of these dynamics. So what do we mean by that? So if we take these measurements and we simply ignore their outcomes, okay, so there is a measurement apparatus that is coupled to the system. It acquires one of these two classical states, 0 or 1. But we can choose, as the experimentalist, we can choose to just not look at it and just keep going, okay, and then just aggregate all the data we collect over all of these realizations without making any use whatsoever of this knowledge. That is a thing we could choose to do. Okay? If we do that, then the effect of these measurements on the system is actually just decoherence. Another way of saying that is that what sets apart a measurement from some kind of uncontrolled interaction with the environment is precisely the knowledge of this classical outcome. If we ignore that knowledge, then we're simply putting our system in contact with a thermal bath, let's say, that is able to go in and change the state of the system in an uncontrolled way, such that after this event, without looking at our register, we simply have no knowledge of whether that qubit is in the 0 state or the 1 state. We must take an average of that. That's what happens under decoherence. And if that's the case, then we're simply running our evolution where we repeatedly inject uncertainty, classical uncertainty, in these events. And this is going to build up in an unbounded way up until the point where the final state we have is completely boring and trivial. Just completely unspecified white noise. Okay? So the core structure of this dynamics is very boring. However, the fine structure, by which I mean this collection of wave functions indexed by their outcome, is actually very interesting. It exhibits this new type of phase transition. Okay, so now I'm going to take advantage of the newly fixed Blackboard. There we go.
Programmable means that it's only digest and how you program.
I'm sorry?
How you put program on the device.
Yes. So we are able to, those blue boxes are the, Schrodinger's equation part. We can also program that. And then we can choose where to make the measurements.
But to make a physical signal for programming, what you will do, I mean, in the real device?
In the real device, this will vary a lot depending on the technology. If you have ultra-cold atoms, you're hitting them with some laser. If you have superconducting qubits, you're sending some microwave pulse and so on to program the interactions between the qubits. Yeah. So we're going to have a conference in 2 weeks where we'll hear from a lot of experimentalists on sort of the latest developments on many of these technologies. But for today, we're going to stay in theory land and just treat these as two-level systems, very unspecified. Okay. Great. So I was saying the fine-grained structure of this dynamics exhibits this novel universal phenomenon, which is a phase transition in information properties of those wave functions. Okay? So the parameter we can tune is number p that controls the rate of measurements. Okay? So what I mean by that is, let's say that after each one of those gates, okay, after each box, we have a probability p of measuring each of the qubits. Okay? So this is a number that lives between 0 and 1, and we can understand the extreme limits first very easily. P equals to 0 means there are no measurements at all. We just have this quantum computation that continues to act coherently for all time, and this will produce a highly entangled quantum states at the end. Okay? On the opposite limit, when p goes to 1, we are making a complete measurement after each layer of time evolution, and this constantly collapses the wave function down to a classical bit string. Okay, so at this point, there is no entanglement at all. At this point, there is going to be a lot of entanglement, and how much? The maximum amount we can get is a density of entanglement of 1 bit per qubit. Okay, so let me label this S of P. It's a density of entanglement measured in bits per qubit. And the striking finding was that this function actually exhibits a phase transition at some finite rate of measurement, okay, separating a disentangling phase from an entangling phase.
Is this averaged over the unitaries or generic?
This is generic, though you can also average it over the unitaries. The important thing is to just perform the average over measurement outcomes after computing the entanglement, which is a nonlinear function and thus does not commute with the averaging. If one performs the average first, we are back to the setting of the coherence where we do not see this. Yes, thank you.
So that seems to be a very special scaling.
Yeah, I mean, I'm kind of drawing it qualitatively. There is a critical exponent here which is higher than 1, so it just sets on a little bit sublinearly, but that's a detail.
Is P supposed to include both how often in the time you're doing it and also where spatially?
Oh yeah, I mean, here it's spatial-temporal density, so on every qubit at every time there is a rate P. You could also modulate it temporally or spatially if you wanted. You might get different behaviors. Okay, so what does this mean qualitatively? Well, if we look at the final state of the system and we take a bipartition between two subsystems A and B, in this phase, this this finite asymptotic density of entanglement means that each qubit in here, even those that are very far away from the other subsystem, will contribute some meaningful amount of entanglement. Okay.
PC is not a different.
No. No, there are universal features of the transition, like critical exponents and so on, but PC can be moved with just changes in details of the model. Yeah. In that particular model that I drew, this is around 0.16, just to fix ideas. Okay, so this is the behavior roughly in the entangling phase. And when we cross into the disentangling phase, instead we get an asymptotically zero density of entanglement, which doesn't mean that entanglement is zero per se, it just means that it's a sub-extensive amount. And so you can think of that as some kind of short-range entanglement where only the qubits that are proximate to the cut contribute some entanglement. The ones that are far away are just entangled with each other. Okay, so they do not contribute. So that's kind of the picture. So how to think of this? Well, if you look at that picture, it is natural to picture this as a network of information that is being built up through these dynamics, where each of the gates is able to kind of propagate entanglement, or propagate information from one qubit to the other one that it interacts with. Okay? Whereas the measurements are able to completely disentangle that qubit from the rest, and therefore inhibit the propagation of information past that link in the network. And so you can view this as a sort of pre-existing network of information that is created by these gates, and then the measurements go in and kind of trim some of these bonds. Okay, so you can have a transition in this network between a highly connected phase, which is going to be entangling, and a weakly connected phase that is going to be disentangling. Okay, so this phenomenon has been studied a lot. It's very interesting. But there is one kind of aspect of it which is a little bit sort of uncomfortable, which is the fact that if we view this phenomenon as taking place in the output states of the circuit, then the whole dynamics that take place beforehand is part of the state preparation. Okay, it's a little bit like preparing the sample for our following experiment. Okay, and a key thing that we demand, across science is that experiments be reproducible. Okay, so if somebody finds superconductivity in some sample, we want to be able to grow a different sample in a different lab that also exhibits the same phenomenon in order to claim a discovery. Okay, so that always needs to be the case. And the problem here is that the preparation stage, if that's how you want to view it, is inherently non-deterministic. Because quantum measurements are random, okay? And if you scale this experiment to even kind of modestly sized quantum processors with a few tens of qubits, you are essentially guaranteed that you'll never see the same bit string twice when you run this kind of experiment. That's because of the counting of how many there are, exponentially many. And so it becomes a little bit problematic to think of this phenomenon as really arising only in these final states of the process. But there is a complementary perspective that has kind of been explored more in recent years, where we view this as a phase transition not in the features of the quantum state itself, but rather in the ability of the experimentalist to learn information from the measurements. This perspective is kind of complementary, but it ends up being equivalent to, sort of mathematically equivalent to this, this phenomenon that we see here. So it will exhibit a very similar phase diagram. The point, though, is that we would like to sort of distinguish these two phases not by a feature of the system, but by the observer's ability to learn. And if you think about what's happening here, okay, the fact that in this phase the system is able to retain this long-range entanglement sort of robustly against measurements, it means that there is some amount of quantum information that is being effectively hidden, a little bit like in quantum error correction. And so it stands to reason to expect that maybe in that phase, the observer is not able to learn as much from their measurements, because the system is kind of conspiring to hide some information. And so here we might conjecture that the learning might be hard, and here the learning might be more efficient in some way. Here, the measurements are somehow being able to successfully disentangle the state and presumably learning more about what is going on in the system. Now, the question is, how do we make this intuition sharp? The good news is that there are some nice frameworks for making this intuition precise. So I'm going to set up a little kind of thought experiment where we have 3 different labs. Okay, so the first lab is Alice. Okay, so this is Alice. She prepares a quantum system in some state psi that is of her choosing, and she keeps that state secret. And she ships it over somehow or sends it over the quantum internet, we don't know, to a different lab, okay, which is Bob's lab. And Bob then takes this unknown quantum state and runs one of these monitor dynamics experiments. Okay, so now I'm not going to draw that whole circuit in detail. I'm just going to draw some kind of box here where these are meant to be measurements that are taking place. Okay, again, this is timing the experiment. And of course, this is a programmable dynamics. I'm going to put all the programming in here. Okay, so Bob has a classical computer that is programming these dynamics. It is sending instructions over to the quantum computer of what to do, which gates to apply. We will apply the measurements. And then in return, it's getting the information about these measurement outcomes on the system. Okay, so all of this classical data of what is going on in the system is being stored in this classical computer. This has no knowledge of psi, though. Okay, importantly, psi came over from a different lab. We don't know anything about it. Okay, and lastly, we have a third agent, Eve, who is an eavesdropper. Okay, and she tries to hack into Bob's classical computer. Okay, so maybe Bob falls victim to a phishing scam, and you know, Eve is able to learn all of this stuff about the quantum experiment. Okay. So again, Eve has no knowledge, gains no knowledge about psi directly. She only gains knowledge about what operations were applied and what the measurement outcomes were. And the question that we want to ask is, can Eve learn something about psi? How much can she learn about psi? How efficiently?
Why introduce Eve? Why can't Bob?
Great question. As we'll see, Bob controls the quantum system, and so in principle could go back later and make a complete measurement on it. We want to rule out the possibility of further quantum operations, and this is just to really kind of lay it out really unambiguously.
Wow, was it Bob behaving classically?
Yeah, we could constrain Bob to kind of give up his quantum computer at this stage. This is just kind of...
But what Bob is reading, he's reading result of measurement, of this quantum measurement. It's not like
Bob isn't doing anything. It's just like an artifact, you know, to separate out this classical knowledge that we have from the actual quantum state.
Off the machine.
Yes.
So that's your definition of learning.
It is one setup where we can ask about learning. By no means unique, yeah. But it's a concrete one, and it has a sharp answer that ends up mapping onto this phase transition. So that's why I'm focusing on it now. So indeed, we can ask, how would Eve go about learning features of this quantum state given this kind of access? Okay, which is a little bit, artificial, but it makes sense because we again want to recover this behavior. And I'm going to focus on the, what happens in this phase diagram at p equals to 1. Okay. So what I'm going to say works literally at p equals to 1, but it works morally throughout this disentangling phase up to the transition. And you kind of have to take my word for it. But so let us focus on this p equals to 1 limit. Okay. Okay, so we have this quantum state psi, we have some one layer of operations, and then because p equals to 1, we are making a complete measurement of all of the qubits. Okay? And what happens up to this point is completely irrelevant to Eve, because at this point we have reset the quantum computer to a classical state that is completely specified by whatever we got here. Okay? So what happens after this is of no importance. So we can simply analyze this short experiment. And this is, again, completely specified by the application of some unitaries here, U. They're drawn from some ensemble of possible operations we might be applying here. And then this complete measurement yields a string of bits, as we've seen before. And the question is, what should Eve guess about the state psi given this kind of knowledge? Okay. So this ends up being very interesting because it maps onto a powerful framework that was introduced sort of in the last few years. It goes by the name of randomized measurements. Or a sort of maybe subclass of very prominent subclass of protocols known as classical shadows. Okay, so what is the idea here? Well, again, Eve doesn't know anything about psi, but given this kind of measurement outcome, knowing nothing else, the best guess you can make at this stage is simply that the quantum system is in this classical state B. It's not going to be a very good guess. You're going to neglect most of the amplitudes, presumably, but it's the best you can do with this observation. So at this stage, we're going to guess that okay, the quantum state here, which notice is the rotated psi, so it's psi after the application of U. We're going to guess that this is equal to the classical state B. Okay? And then we can backpropagate this guess down to this point, so the original state of interest. And that means we're going to guess that psi is this state. Okay? Again, not a good guess, but it has some little kernel of truth, okay, which is the fact that we sampled this bit string not uniformly at random, but from the Born distribution of this particular state. So it correlates with the true state a little bit better than random. Okay? And so in particular, it was shown that if we now, so what Eve has on her classical computer is this collection of guesses for the state psi. Okay? Presumably, the experiment happened many times, and Eve gets to look at the whole record, and so she has a collection of these. And by aggregating or averaging all of these guesses, it was shown that one finds the true state, psi, up to the application of some noise. Yes, yes. So this is the meaning behind this name of classical shadows is the fact that we have this unknown state, which is an object in a very high dimensional space. And what we're doing is, in a sense, rotating it in various ways and taking a snapshot of it. So it's like doing some kind of imaging where we are collecting the shadow that this object casts on various surfaces, and then we're stitching these surfaces together to reconstruct this higher dimensional description in an approximate way. Not at this level. This is all, the bases are chosen uniformly at random among some ensemble, and we just have this collection, and we make this guess. Yeah. I mean, I guess in some sense, yes, you could find this guess by minimizing some cost function. In this case, it's just very obvious, but of course, one could have a more complicated setup. Yeah. Right. So again, we have a little bit of signal, which is this true state, but then it's kind of drowned in a sea of noise, okay, which is the fact that these measurements are very random. However, this noise is completely specified by the choice of random rotations that we made. It does not depend on the state psi. It's fixed once and for all by the setup of the experiment. And so at the level of classical computation, Eve is able to undo this noise. Okay? Maybe this is not a physical operation that is legal under the rules of quantum mechanics, but there's no harm in doing it on a classical computer, simulating it. Okay? So this way, Eve is able to get a set of estimates of the state psi that let her learn a lot of different things.
Missing something. In this circuit, you are averaging over 2-qubit uniphase?
Yes, this is specific to this particular setup, but it could be single qubit. Yeah.
Yeah, I mean, you have these
Right. Yeah.
So, but if we measure then over the tensor product of halves, I mean, 2-qubit, suppose I change a bit in my B. Couldn't I absorb this change in my local measure, and so it would be invisible?
Right. The key thing is that this is a quadratic thing, so there is a forward evolution that happens on the quantum computer and a backward evolution that happens on the classical computer. And if you absorb a bit flip into the measure, it comes out the other side. So it's not it's a second moment quantity. Yeah. Good point, yes.
Is Eve allowed to know like the correlation between the unitaries that were performed and the outcome? Does she see the circuit?
Does she see this? She sees this part of the circuit, yes. Yes. So these come in pairs. Each U is associated to its own outcome B, yes. Otherwise, you don't see anything, yes. I don't think you see anything.
Like, the thing that you said at the end, it was not clear that she actually needed to know the individual U, right? She knows the noise channel. That only depends on...
The noise channel arises from averaging exactly these things where each U is paired to its own B. Otherwise, it does not work. Yes. Good. Yeah, good question. Thank you. Okay. So from running this kind of approach, Eve is able to learn in this phase efficiently in the sense of as efficiently as Bob. So Bob gaining this additional quantum access at the end provides no substantial advantage to him. Eve can do just as well from her knowledge. And in this phase, instead, we find that Eve becomes exponentially disadvantaged over Bob. So Bob having further quantum access to the system provides an exponential advantage. What that means precisely is that the key measure here is sample complexity. Which is a technical way of saying number of experiments that are needed in order to learn something with a given confidence. And what happens in the entangling phase is that Eve is going to need a number of experiments that is exponentially larger than Bob's by this amount here, 2 to the power of n times this quantity here, which is basically the order parameter of our entanglement transition. So it sets on at this point, and it immediately becomes exponential. Okay? So this is a precise way of quantifying this transition in terms of learning. And I should say this line of, this approach grew out of prior works where the learning is a little bit more intuitive, has more of a classical flavor to it, where one is trying to learn the value of a conserved charge in that system. So making these measurements of the charge density and trying to reconstruct the total amount of charge in the system.
I have a critical point.
Yeah.
Is the sample complexity scaling differently or is it the same?
Okay, so what happens here is interesting, and it's not captured here, but really there is something I'm sweeping under the rug, which is the locality of this randomized measurement. So at t equals to 1, you recover exactly local randomized measurements. And then as you move away, you recover something that at the critical point looks very much like globally randomized measurements. So there are different quantities that are easily learnable, for example, fidelity, but not local powers. But it's basically still as good as Bob's. And then as you enter the entangling phase, you get the separation. Yeah. So something is changing, but not, yeah.
When you say you learn something, like, is it like all some kind of low weight operators or?
So it can be different things, right? So again, out here, the thing you learn very easily is local operators. And then here, the thing you learn very easily is, for example, global fidelity. Fidelity with a pure state on the whole system, for instance. Then there is entanglement entropy, which is not efficient. Okay, it's exponential, but it's still kind of state-of-the-art method for doing it. You can do it in this phase. In this phase, everything is going to become exponentially more costly. Okay? Yeah. So that's what we mean by inefficient. Yep.
What does E do as you move away from P equals to 1?
Sorry, what does if do as you move away from P equals to 1? Right, so good point. So there, as long as you're above, let's say, 0.5, there is a percolation transition where it still effectively looks like locally randomized measurements, just with some kind of, not just one gate, but maybe some small circuit of gates. Below the percolation transition, it really is a little bit more complicated. You have some kind of global operation that you need to deal with. And Eve would need to run some kind of tensor network simulation of the second moment channel. Yeah.
My question is even more naive.
Okay.
You don't measure all the qubits. Eve doesn't have a state to start with.
Oh, you just run up until, you can run for a longer time, so you have access to this whole experiment. Here we stop at 1 layer because we make a complete measurement, and there's no reason to go further. But if you don't do a complete measurement, you keep going. Okay? And then what Eve does is she would start from the maximally mixed state at the end and backpropagate it through this circuit. And this may or may not purify. But you can run the same exact machinery.
Then how do you justify that starting from a maximum state?
It's like a flat prior. You could take different priors, but that's a natural one. Yeah. Okay, in the last 10 minutes, I would like to kind of wrap up by focusing on a slightly more general question. Okay, so here we have a transition in learnability, but it's dictated by the specific setup that we considered. It's a little bit artificial. I mean, it's nice, but one can ask the more general question where if instead of artificially limiting Eve's access to the system, we just do the best we can. What can we or can we not learn? So here, I'm going to try and draw something. It's going to Okay, so we want to ask the question in particular, as we become able to create more and more complex quantum states, presumably this means that also learning their features becomes harder, and so we want to know where the boundary lies. What is and isn't efficiently learnable in general? So what do we mean by complexity first? What's this notion of a complex state? The natural notion for complexity is basically the time taken to prepare a quantum state. Okay? So if I have a certain quantum state psi, I can try to sort of reverse engineer a quantum circuit that prepares it. Okay, and so on and so forth, starting from some simple input state. Let's say all 0 conventionally. And the time taken to prepare this state is sort of optimizing overall possible strategies. The shortest one is going to be the complexity of that state. How do we measure time? Conventionally, we measure it by counting layers, okay, so that the overall time constant taken to apply these gates on the individual technology you're looking at is not relevant. We really care about what is known as the depth of this circuit. Each layer is 1 unit of depth. Then you concatenate many layers, you get some higher depth circuit. So motivated by this word depth, I want to lay out the problem in terms of kind of arranging these states of different complexity as kind of points in an ocean, okay? So different levels of depth in the sea, if you will. Okay, so here is our axis of depth. We have the surface of the sea is at 0 depth, and these are very simple classical states, like all 0 or things like that. And these are obviously very easy to learn. Okay. And then we can keep going deeper and deeper. At the very bottom of the ocean, we have states of exponential complexity. Okay? So these are states that are very, very hard to prepare, and as a consequence, they're also very hard to learn. So if somebody gave you one of these states with a complete list of instructions for how to make it, it would still take you a very long time to verify that. So proportionally, it would be harder to just learn if they just gave you the state. So we want to think of this sort of this bottom of the ocean as a very, very sort of dark place where learning is very difficult. Okay? So then we have various other landmarks that we can ask about. For example, polynomial depth, or logarithmic depth, or sort of constant non-zero depth, let's say. And so, okay, so we have the sun, okay. All right, and the light of the sun represents our ability to shed light on this phenomena, okay, at different depths. And it tells us that things that are near the surface are easy to learn. We can do it. We have, of course, these classical states are very easy. There are also efficient learning protocols for states of constant complexity that are quite general. And then, for example, these randomized measurement tools can be pushed to learn many things, for example, up to logarithmic depth. So we know that sort of the light here illuminates features down to a certain depth for sure. And we can try to push these protocols further. But a complementary perspective that I want to advocate in these last couple of minutes is to try and kind of take the antagonistic perspective of trying to hide things and kind of push the darkness upwards. Okay? Maybe that's something that we don't want, but maybe that's how nature behaves. We would like to find out. So it might be beneficial to take the perspective of nature and ask how well could you, in principle, hide information from physicists, from experimentalists. And this question of hiding information leads us to cryptography. Okay, it's the science of hiding information. There is a quantum version of cryptography that tells you how to hide information better using the laws of quantum mechanics. And in the last few years, there have been very interesting developments, particularly around the concept of pseudo-randomness. that allow some interesting applications to physics in precisely in this language. Okay, so I'm not going to say much, I don't have time, and it's a little bit too technical, but the idea is that there are families of transformations, okay, so families of unitaries, that are efficiently preparable, okay, so they live somewhat close to the surface, okay, they're physical, they can be prepared in realistic time. They're indexed by some key, okay, this is the cryptographic concept, okay, and so if you know the key, you can make them and you can undo them, that's fine. But if you don't know the key, and you're just presented with an experiment that features copies of this unitary, sort of acting on the system, and you're asked to distinguish, okay, so this ensemble of pseudo-random unitaries versus an ensemble of genuinely random unitaries. Okay, these are things that live at the bottom of the ocean, extremely unlearnable, extremely complex. You are just asked this question of basically testing this hypothesis, A versus B. There are very rigorous cryptographic arguments to believe that this should not be possible. Okay, so this rests on some cryptographic assumption on the quantum security of some one-way functions and so on, but you know, it's very strongly believed that this is the case. And this shows that there exist states that live, for example, here at polynomial depth that are not easily distinguishable from states that live down here. Okay? And so this means that essentially this darkness has to stretch, you know, quite far up. Maybe it doesn't cover the entire space, but certainly many states at that level become as featureless, as unlearnable as things that live down here. And then the very last things I want to say, if I have time, I think 2 minutes, is that the recent results from about a year ago show that these pseudo-random unitaries can be made even simpler. Okay, so in jargon, this is described as a shallow PRU. So this is a process that lives just below logarithmic depth. So let's say here, this would be polylog, which to fix ideas, we can take to be log squared. Just a little bit faster than logarithmic, a little bit deeper than logarithmic. But you have now states that are here and are also themselves indistinguishable from states all the way down here. Okay? So the message is maybe a little bit unsettling. It says that there are many, many things that we cannot learn, and that maybe, you know, the best we can do by pushing these learning approaches down from simple states is actually quite limited. And there are many features that can be hidden securely in a way that you know, doesn't matter how clever you get, you're not going to be able to resolve them. Now, this is not the end of the story, of course. This is taking a bit of a maybe unrealistic black box type of model where you're just given this kind of access to the states without any additional context, which maybe is not what happens in a physics experiment. But I think it is a very interesting kind of development to keep in mind as we continue to sharpen this frontier between what can and cannot be learned in realistic experiments. I think I'll end here, take any more questions. Thank you.
Maybe like to play devil's advocate, like a potential takeaway from like what you described as pseudo-random unitaries is that actually depth is not a great proxy for learnability. So is there something which is like more directly has like everything below this like metric is unlearnable and everything above is learnable?
Right, that's interesting. I don't expect such a universal kind of invariant to exist because there are, of course, many exceptions, like here I'm being schematic again, but there are, for example, stabilizer states that are learnable, even though they can have quite high complexity, not maximal, but Gaussian states can often be learned efficiently, things of that nature. So there are various exceptions. And of course, this means that this one axis is not the end of the story. But even though these PRU constructions are a little bit fine-tuned and contrived, my sort of gut instinct is that this should be quite generically true for sort of randomly sampled things at that level of complexity. So I think this is kind of a good proxy to a zeroth approximation. Keep in mind.
More questions? Yes.
Should I at all be thinking of this in terms of like Hamiltonians? It's just like kind of crazy also all Hamiltonian, very chaotic.
Mm-hmm.
And I just wanted to log in time on how that introduce
Right, so Hamiltonians have a lot more structure that might make this harder. There are actually papers from like 2 days ago, very timely, that show basically some no-go theorem for Hamiltonians of constant locality. Like there is always some residual feature of locality you can detect after a short time. But also they show that you do indeed succeed in hiding everything if you have polylogarithmic locality. Maybe that's not so physically realistic, but it sets a boundary.
Any more questions? Okay, thanks very much.
Thank you.